Hello there, PrintShift back with the large bed conveyor, aka PrintShiftXL. Got machine in here. I've been working on this platform as a development on belts themselves in preparation to move PrintShift part ejection system to larger 3D printers. This particular machine is Core XY my own design. Not gonna be bringing it back. Figure we move it to a Voron, a PrusaXL, or even an Ender 5. Just show you what we're talking about. Belt ejection system. So we have capped on surface, under tension, driven by some motors in the back, in a Core XY. Super exciting. Today, we're looking at belt testing. How do you measure the performance of the printer's belt? What we're gonna do is, for that is what I'm calling the Belt Deflection Tester. This isn't the only relevant test for a belt, not by a long shot, but it's something that I believe is important to the performance of larger and especially taller printers. There's a big shout out to Eric Duncan for the spring bit. He's one of my Patreon supporters, and a huge shout out to all the other Patreons scrolling down below. Makes it easy for me to acquire fancy measuring devices, but I still want to support people building their own systems at home, which is why we're going for a visual metric. It's not as accurate, but more on that later. Anyways, this update took a bit of fiddling to get working, and there's room for improvements, but I want to do a quick video on it and the testing thereof. The idea is to test how much force it takes to bend the belt sideways. Basically, how much force it takes for your print to start wobbling and detach from the bed. This force is applied by the nozzle, moving back and forth over your part, and it's basically a drag force. It's relatively low, but generally over time, the taller your parts, the more wobbly you get, and the less likely it is to stick. Now, usual fix for this, put in a big old brim, get your part to stick better. Not a problem, but here we're trying to measure, improve, and get a belt that works better than the ones we have now. This is a problem for all 3D printers, parts becoming detached to the bed, but on a traditional machine, you're only talking about bed adhesion or warping. Here, we're trying to focus only on the belt, so we're actually going to be taping the tester down in order to see how much force it takes to pull up one side of the belt. On this guy, we got a full Cartesian 3D printer, so we have force measured in two directions. On most angled belt printers, you're only going to have force heading in one direction as we're printing, so it's basically only measuring along the belt. You can see some pretty clear signs of deviation. Parts getting more and more wobbly as they get taller, and then this guy was starting to actually shift over. Eventually gets caught by the nozzle and eliminated. Lest people think all printers, this was having trouble where the belt itself failed. Throw a shot of that in there, why not? The belt deflection tester consists of two printed parts, the pyramid and the tensioner. This is designed to take a spring and screw setup so we can easily measure and see the force required to pull the pyramid to the side. It's not much. This spring maxes out at 1.75 pounds of force to pull this way. That's about 0.8 kilograms. The reason we're using such a lightweight spring is because the minimum force the spring can measure, the force it takes to move it to open up even a tiny amount, is 0.18 pounds force, 0.08 kilograms, which is why we have these guys. It's a superior readout. This is a 50 Newton digital force gauge. It can measure down from basically 0.01 pounds up to about 11 pounds. What's 50 Newtons in pounds? I don't know that conversion, but basically can measure the same sort of thing. Nice digital quick readout, but about 50 times more expensive than a spring. So, if you're doing a lot of belt testing, not the worst idea. But for today, we're going to be checking the viability of this guy. Visually, I think the springs come across more easily. I'm going to shift over to the printer, get this installed so we can start poking at it. I set up a 1 pound plumb bob, sort of demonstrate the spring measure. I forgot to set up the camera and see if I could get it in frame or anything. Let's see what we can do. That looks pretty good. And yeah, it's a little silly to hang a plumb bob inside your 3D printer. This is just clickbait for YouTube. Whoop. Good enough. But you can see our spring. This is a copy of the spring that I have installed right here. He's under 1 pound of force from this brass plumb bob. Why do I have this lying around? It came with my house. I've never actually used it for anything but this. But hey, it's pretty. All right, we're going to measure the length of the spring. I know the spring constant is 0.029. That's pounds per millimeter. Yes, I'm sorry, the units are weird. I got these from McMaster. I could do all the conversions up front, but I prefer to use the rated numbers and then convert afterwards. So to measure how much weight is on there, I'm going to measure the current length of the spring. This is end to end based on original length, so that's about 61 millimeters. The original length of the spring is 27.7 millimeter. It's 5.5 millimeter diameter and 0.5 millimeter wire. The spring constant is 0.029. So 61 minus 27.7 is 33.3 times 0.029 is 0.9657. So it's measuring this at a little under a pound. Now let's see if we can frame and measure the weight with our digital force gauge. Come here, buddy. Oh, framing. And it's upside down, but the digital force gauge says our spring is reading slightly under, but it's pretty easy to see. And actually, let's put the spring up and measure the spring too. So you can see the elongation of the spring. Even bouncing it, the spring gets longer, our readout gets all wonky. But that is the theory. Now we can measure, stick this to the bed, and measure the force it takes to deflect the bed. Now this printer is tensioned by springs as well, so I can adjust the tension on the belt and see how much force I'm putting on the belt with these beefy springs. So we're going to start it at about 10 pounds force. Let's see. Set the camera up so we can see both. That looks reasonable. So I'm going to hit this down with double-sided tape. And my scissors are gone, of course. Right back. So I think we might want to move the camera lower down so we can see the deflection. So what we're trying to measure is, ooh there, no escaping, the amount of force it takes to bend the belt. You can see the belt is actually deflecting up. Well, we'll have the camera watch the tester, and then I'll just tell you what the tension is on the belt, because I'm not sure how to do this otherwise. Good sort of look at the tension. So I'm setting this down to 10 pounds force. So it should be 24 millimeters. Total length of the spring is what we're measuring. 24, all right. Same thing on the other guy. And so we can hear the belt. Fairly low tension. See, there's even a little bit of spring in it already. But, all right, so we have the small gap. We're gonna measure as soon as we start to see that going in. We'll see the deflection. So we're at less than 0.18 pounds now. And the goal is to get this down to a millimeter so that we're not bottomed out. So basically we're measuring. So now the length of our spring, end to end again. 36.2 millimeter. Let that go, it'll pop up. I'm just gonna write that down and do the math in a minute. I'm gonna swing back over and increase the tension on the belt. You can see we're compressing the spring. We're going to compress it until there's just a tiny bit of gap in the springs, which will get us to 50 pounds force. And the other spring, I'm not gonna bother turning the camera for you because reasons. When we switch back over the tester, now you can see our gap is opened way up. And in fact, we need bottoming it out at 2 pounds force to get all the way in. Switch to a higher force spring. Try and keep my hand out of the frame. That looks about right. You can really see the tension put on there. So that's 32 millimeter total length of the spring. And yes, that's similar, but the natural length of this spring is a good bit smaller. So we're still getting good readings. Once more with the digital force gauge. I set the units 2 pounds just to keep it consistent in the video. I understand Standard works great, but can we still see it in frame? We have the same measurement of getting within a millimeter, about half a pound, which is about right from our spring comparison. And then increasing our tension to close to a maximum, up to just over a pound of force. And that would be the force that the extruder is exerting on your part during printing. That's the force that we're trying to increase. The model for this is up on PrusaPrinters, link down below in the description. I got these springs from Camaster, but any looped end spring would work. You just need to measure the starting point elongation so you can calculate the force involved. Now, there are many options for belts. I've got a few on hand. We'll be testing them out on that machine. Also have a few other belt printers that need a few fixes and upgrades. I'm gonna swap out this guy and run some tests on the tiny belt, and the baby belt. So, that's of interest to you. Feel free to like and subscribe, and thanks for watching. Happy printing, guys.